Okay, so let's start. I want to basically start with just a remember constant administrative announcement. Midterm is March 21st, 7 to 9 p.m. One sheet of notes, handwritten, both sides is what you can bring. Everything else you have to have in your head. The project information will be released today. The important thing is we're going to have you. The project requires you to work in teams of 4. There are other rules and stuff that we're going to describe. So team size 4. This will be released later today, right? Team size 4. And to make sure that you are appropriately on track for it, we're going to have you sort of do team forming next week, and then basically submit a proposal the week after. Because we know the exam is coming, we don't want to make you submit a proposal right before the exam. So the proposal submission is after the exam, basically right before spring break. Very short. Proposal is not like a big thing. Then what we're going to do is the important thing is that after you've put your proposal in April, so after spring break, by the second week of April, we expect you to have made sufficient progress on it so that you can have meetings, mandatory meetings with core staff to kind of go over and get feedback on how you're doing and sort of how you want to take it till the end. By the end of April, which is the end of the term, we expect you to submit what you've done in your proposal, in your project, and then you will be expected on a very short turnaround to review the work of other groups. So everyone has to do your work and has to review. And then by, I think, middle of RR week, we expect everyone to take in the feedback into account and submit your final versions. So the project is going to occupy a lot of your time in the month of April. I strongly encourage you to get a head start on thinking about it so you can kind of really get what you want accomplished. We will lighten the homework a bit during that time to give a little bit more time, but there's still topics we're covering, so homework will have to continue. The midterm, again, we're going to release homework today that's going to cover the material kind of that we talk about today and on Monday primarily. Small dependence in that homework on material that will be happening on Friday because it's due then. That homework that we released tonight will be in scope for the exam. That's important to know where exam scope ends. So you should have, our goal in this course is that if you do the homework, attend lectures, attend discussions, you should have to do no additional studying besides making your sheet of notes to do the exam. There's no like hidden curriculum of things you need to study or anything. It's just we've given you everything you need for the exam. Okay. Any administrative questions relating to project or exam? I want to make sure I acknowledge those. None? Great. Okay. So today I want to talk about something you've already seen a little bit in discussion. I want to acknowledge it more on sequence to sequence, and we'll start into the attention mechanism, which is the heart of the transformer architecture, which is what we're building up towards. So we've talked about these sequential processing using a neural net by using RNNs, right, and layers of RNNs. So these are filters inspired by things like, learned common filters. And so they fundamentally have a real-time character to them because they inherit this from their intellectual source, which is common filters. which means that when something comes in, they take an input in and they produce something. And they kind of go sequentially doing this. However, there's lots of natural sequential tasks that where the data is sequential in nature, which do not have this hard real-time requirement. And so we would still like to use these recurrent neural net or these sequential type structures for those problems because they're practical problems. And so we have to figure out how to do it. So classic example, so consider translation from one language to the other. So if you're going to consider translation from one language to the other, the idea is that first, language is sequential. Language data, at least, is sequential. You have one word after the other as part of your data. So it's natural to think about using a sequential model. Sentences have variable lengths. And paragraphs have variable lengths. Words have variable lengths for that matter. So it's natural to think about things in a sequential type of model as opposed to a connet type of model, which you've seen is kind of fundamentally, natively something which has a fixed size. The problem is, language is sequential, so you can use these RNN type models, but different languages can have different word orders. So for the same sentence, you can't just translate everything one word at a time. So one word at a time translation doesn't work. So the problem is, if you try to use a sequential model in its most native form, where it takes in some input, takes in the past state, and generates a new output, that can't do machine translation. Any questions on this? Hopefully this is intuitive, but I want to make sure everyone understands this challenge. Right? Because you might have to reorder the words. You can't do word by word. So what do you do? So these kind of problems, right? These problems naturally take an entire sequence as input and emit an entire sequence as output. Hence they're called sequence-to-sequence problems. Sequence in, sequence out. So the question becomes, how can you use like an RNN type of structure to solve these problems? So just a little bit of a preview. We're going to talk about this in a semi-historical fashion, because I think it's actually not a bad way of introducing the ideas. And the ideas we're going to talk about here, first, we'll talk about them in the context of RNNs, but as we build, maybe by a week from today, we will have introduced the transformer architecture, which will no longer have RNNs in it. But a lot of the ideas that we're talking about architecturally are still relevant for how you think about the problem. So the idea to solve these problems is called the encoder-decoder structure. So the idea of the encoder-decoder structure is you have one neural net that sort of takes the data and takes it as input. takes the language, for example, for translation, it takes the sentence you want to translate and it eats that sentence, right? It sort of consumes it. And it takes all the information from that sentence and it represents it into state. That's called the encoder. And then you have a decoder structure, which is another sequential processing thing, which starts with all of that information and then emits the output. Okay, so visually, it's like this. We have 0 coming in, some initialization. You have the encoder, which has a recurrent structure where inputs, words from the sentence, for example, come in, the state gets updated, another word is taken in, state gets updated, and this keeps happening. Until you run out of input. Then you take this state, right? This entire thing is the encoder. This is a sequential neural net. And it passes over to the decoder. And the decoder is run in a different way. So notice in this encoder, all you cared about in this classic picture, there's no outputs. There's just inputs. The only thing that's happening is a state is getting updated in the encoder. The entire state is then passed to the decoder. The decoder has to actually generate the output sequence. Right? So we're going to need outputs. So we're going to use the sequential structure of neural net structure, which means we're going to have weight sharing across these different time instances. So when you have the decoder, so the encoder knows it's starting because it's gotten a 0 in. So it knows it doesn't know anything yet. Okay? And then it gets input. So the decoder, however, is handed this state. So you usually start the decoder with an input that says start. A special input called start. Right? Then the decoder emits the first output, y1. And now you take this state and you pass it, you pass it on to the same neural net again. So decoder is also a sequential neural net with weight sharing across the different steps. But now the question is, what's its input? So decoders are run in what's called an autoregressive mode. So autoregressive is a word that comes from signal processing and statistics, and from the idea that when you think about regression, you have like, what are you using to make your predictions? Autoregressive models are one in which you use yourself, your own outputs, to also make your predictions, right? And so they're in sequential. But whenever you have a state, something you feed back to yourself. So autoregressive mode means that you take this y1 that you emitted, and you also make it the input to the next time step. Then this thing emits a y2. And this continues. So you saw this in discussion. And typically, in the context of, like for example, translation, you also have if you're going to have a variable length output, whenever you have a variable length output, you need a symbol that says end, right? So, for example, you learned this when you learned about how you have strings represented, right, in arrays, right? You null terminate them. You have a special character that means end of string. So here, there's a special character that typically means end. And then you just don't feed it into itself again. Just stop. This is the encoder-decoder structure. Any questions on the basic structure? Okay, so you have an encoder, pass in the input, you have a decoder, and it emits output. Yeah? No. So, for example, the last thing will be end token. That's when you stop. You stop with an end token. Okay, so now inside these boxes, right, you have one neural net on this side and a different neural net here. You don't have to have weight sharing from here to here, right? This is not weight shared necessarily. So inside this box, like what's inside the box? Right, inside the box is, in an RNN context, you have an RNN. One layer, then another. Layer 0, layer 1, and so on. And the whole thing, all these different layers, hidden state, is the state that you pass on. So you have one such thing inside the encoder and a similar such thing inside the decoder. Except there's definitely a head on top that emits an output. So again, if you're doing this passing of the state onward, you could just, from the encoder to the decoder, you could just pass the entire state, or you could pass it through a multi-layer perceptron, right, to transform it in some way for the appropriate input for this side. Kind of doesn't matter, but it's a choice. So first, a comment on training these things. How do you train this? If you have a bunch of examples for sentence translation, you have a bunch of input sentences and output sentences, and you want to train and learn these weights. The way that you do it is you train it the way you would train anything else. You put in the input here. You add a loss layer on here, and you measure the loss. But there's one trick for training, which is for training, for supervised training, you know what the output is supposed to be. So you make sure that this thing on this side is the output it's supposed to be. And you apply the loss here. You don't necessarily feed it in. Is that clear to everybody? So in a way, the training of this thing is exactly like how you would do training for system identification, right, on the decoder side. Right? You just predict the next thing that's supposed to come out, but the previous things are what you actually put in. Okay? So you do that, put a loss layer on top, you have gradients, you can train, and you just train. Nothing particularly special there, except the fact that you typically will put in during training, you'll put in the actual desired output here, and you put a loss on top. Any questions about that? Yeah. Great question. So the question is, so during training, so let's just do an example, right, of this. So during training, suppose the desired output was I see cat. Okay, that's the desired output. So how do you train for this? So first, for the first symbol, your loss is going to be on actual output, call it y1, and I. The second one, the loss is between actual output 2 and C. And then this loss is y3 and assuming we're doing it kind of, that word by word. Next loss is between y4 and cat. Okay, so far so good, right? Now, what are the inputs? During training, the input here is start, because it's always start. Of course, there's something here that's coming from the encoder. Let's not worry about that. The input here is actually I, because you know that's the desired output. Okay? So that's what should have come out of here. So you put that in. Then the input here is actually C. And the input here during training is actually a. So now the question is, why doesn't this allow for cheating during training? So by cheating during training, I mean, I'm giving the decoder I see a. Why can't it just say I see a for the first three things? And you can see it by looking at the arrows here. Okay? Does everyone see? By the arrows. The I comes in here, and there's no arrows going from this side back into here. So there's no way for this I to actually contaminate what's happening here. Okay? So this is just, everything is causal in how it's being processed. Yeah? What about the initial? So the initial hidden state is coming from the encoder. Right? So there's the initial hidden state is H from encoder. Yeah, great question. The question is, when you do backprop, how does backprop work? So the losses are all sitting here, right? All the losses are here in a sequence-to-sequence problem. They're propagating gradients back through everything. Okay? So the combined effect of these losses are going to put pressure on this hidden state to say, please, I would like you to be different, hidden state. And then that desire for that final hidden state to be different will backprop through the encoder to make, do weight updates through weight sharing on all these different time steps. Because this hidden state will say, I would like to be different. Okay, how does that propagate to the hidden state from the last one in terms of gradients using backprop? And then how does that then propagate backwards again and again and again and again? So each of these will then say, I would like to change my weights inside of this network in some way. You apply the sum of all those changes. Standard weight sharing. Okay? Yeah. So the question is, what if during training you actually fed this y1 into here instead of I? That's the question, right? Great question. So if you do that, what'll happen is, in effect, this thing has learned the wrong thing at first. Like, it's just wrong at the beginning. This is sharing weights here. So now, you've made the job here much harder. Because instead of having a clean input, I, you have a noisy input, y1. Okay? So this is a challenge, to have this noisy input y1 coming over here, which makes this thing have less high quality gradients. Now you're going to do weight sharing. Remember, all this is weight shared. So this this poorer quality gradients here, and the even poorer quality gradients here, and even poorer quality gradients here are all going to be applied to the weights. So that will typically at least slow down training here for what's happening here. But you might say, wait a minute, we had a homework problem, and our homework problem told us that if we have noisy inputs during training, this has a regularizing effect. Remember? You had which is basically saying that you shouldn't maybe depend, what's that regularizing effect? The regularizing effect of doing noise on your inputs is to say maybe you shouldn't depend that strongly on the details of these inputs in deciding what your output is, right? How did that manifest in the homework? That manifested as basically acting like ridge regression, which says don't have a strong dependency on any individual thing, right? Because ridge penalizes the size of the weights, which is strong dependency, okay? Is that clear to everyone? Recalling what you'd learned before. So based on that, you might say that, okay, maybe, and you can imagine, if we made you do a homework problem, which we did not make you do, of actually simulate noisy input training of a least squares problem, you can imagine that convergence would be slower, right? Because you have some more noise. You have to average that away, okay? But you converge to a better place if you think the ridge regularization is correct. Everyone with me? So your question is basically can be viewed as asking, well, do I want to get that effect here? Like, just because something will make the inputs noisier and make the gradients noisier doesn't necessarily mean it's a bad thing to do. Okay? Like maybe it's something you want to do. And the answer typically that many people will use in practice is that they will randomly sometimes actually send this through during training to get kind of both effects. Sometimes you let this come through, and sometimes you just put in this thing. What that does is it helps this thing be less dependent on the details of this and more robust to the actual outputs it actually tends to generate. So if there's directions of variation that this thing tends to use, you want to make sure it learns to not to depend on those appropriately and not be too sensitive. And you get that effect by feeding this in. So this is done. This is a trick that's also used in RL problems quite a bit. But RL is out of scope largely for this class. But the idea of sometimes feeding in sequential settings the previous thing, even when you have supervision, is valuable in practice, but not all the time. Yeah, question? Mm-hmm.
But what is, like, it seems to me that noise.
Okay, great. So the question was, we're talking about language as the motivation here. And images, when you have noise that you add, you can imagine the neural network experiencing similar or related noise in actual practice and deployment. And so it's kind of, you can think of it as a data augmentation designed to make yourself be respectful of the regularities you want to see in the real world. Okay? Which is that sometimes things are noisy. In language, at the end of the day, you don't actually send in words, right? You send in a vector, because everything here is vectors. So some word-to-vector translation that we're not talking about here. And so adding some random noise here is going to be, coming out from whatever this thing output is actually going to be some disturbance in that vector space, which need not correspond to any natural disturbance that you might expect to see in practice. Here's a little different, because here practice of the decoder is really, this thing only sees the input from the last thing it said. So it's maybe not so unrealistic, like it is the kind of thing that you expect to see. Okay, but in language generally, like how do you, the bigger question you're asking is what is the nature of data augmentations that capture natural variability in language? So that's a great question. I will leave that to the NLP classes to answer. It's actually pretty sophisticated for what kind of augmentations are used for language. They're not as obvious as the natural ones you do for images. Oh, add some noise, remove the color, rotate, twists. They're more interesting distortions that one does for non-language data. Yes?
Is there ever going to be a case where, like,
Oh, it's a great question. The question is that when you run the decoder and you have a particular desired sequence you want to have, which is I see a cat end, right? What happens when the output, so I'm going to continue this. So here is loss, 5, end token, whatever it is. So use the word token. Token is what we use for language things to make it, they're basically like words, but you need to make sure they have total coverage. So we call them tokens. We'll talk more in detail about this later. I don't want to get bogged down in the NLP stuff right now. So during training, you do this, right? So you include the cat. So the question is, what if the thing you actually emit here is not end, right? What if the thing you actually emit here is something else? Then what do you do? So the natural solution to this problem is say, well, whatever it is, don't continue. Because this is during training, right? We know what we're supposed to get. So don't actually run something with end as an input. That's the easy answer. You would say that, wait, I'm taking away the sometimes I introduce noise into the next thing. I introduce the actual output in the next thing. So yeah, you just don't do it here for end. Because you're right, if you ran it, you would have nothing to put in the loss layer next. So with nothing to put in the loss layer, you could just keep running it, but you get no gradients from that because you have no loss. So yeah, good question. Yeah. What if you end early? So what if this thing actually has chose for y3 end, right? And you wanted it to actually continue, right? So again, it depends on what you're doing. So if you're just doing the standard approach that we're teaching you, if you actually just use the desired sequence here, there's not a problem. You just have a loss between end and which is fine. If you choose to actually send it over, right, because you're randomly sending things over to make it more robust, you'll send an end in, and this will still have a loss to cat. Like, again, nothing breaks. It's an input you never expect to see, though. But that's fine. There's like no problem with seeing inputs during training that you never expect to see during actual use. The problem is the other way. When you see inputs during actual use that you've never seen during training. Like, that's bad. Yes?
I have a question about...
Sure. During training? Yeah. Okay, so during training, the encoder looks like this. Okay, suppose there's only 3. So you have some language in which there's like a token that comes in that is like translates as a word that translates to cat scene. Okay? And the second thing is some language where the word is by me. Like a special word that means cat scene and by me. That's the whole sentence. Okay? And then end of sentence. Okay, that's the encoder, and then out pops this hidden state. That guy. So during training, you feed it the input you have, cat scene, by me, end. And the gradients flow back through here, into here, here, and here. You have weight sharing, so there's some weights here, some weights here, weight encoder, weight encoder, weight encoder. Here's weight decoder, weight decoder, weight decoder, weight decoder, weight decoder. So you get gradients on weight encoder from all these 3 things, apply them as usual. Standard PyTorch, Let PyTorch do it with weight sharing. This is end-to-end training of sequence-to-sequence models. Supervised learning, standard, pass gradients through, have the weight sharing as you need it. Everything just works. Okay. So far, is everything clear and good? Yeah.
How do we evaluate the loss work? So the YIC.
Okay, great. So let's talk about the loss. Okay. So let's think about these losses. So for language data, language problems, how to pick loss. Right, that's your question. So you're right. Before you pick a loss, you have to pick a representation. Okay? So first problem, subproblem. Representation. So for the representation for language type problems, you typically say, we have basically two categories of problems. We have problems that are regression-like in nature, where we're trying to predict a continuous value. And we have problems that are classification-like in nature. We're trying to predict something from a discrete set. Everyone good with this? Important to remember. The first question is this like regression or classification? So here we'll just take a vote. For language, is linguistic output like classification? Raise your hand if you think it's like classification. Okay? Okay. How many people think linguistic output is like regression? Raise your hand. Okay, so we seem to have a kind of split. How many people think linguistic output in the real world is like both? Raise your hand. Both, okay. How many people think linguistic output is actually sufficiently different to be like neither? All four possibilities, right? A couple people are willing to say neither. Okay, so here we will follow deep learning philosophy, okay? So you can take a glance at what is actually true, and you say, well, actually, if you think about spoken language has some aspects that are well approximated by discrete, namely specific words or phonemes, right? And other things that are actually pretty continuous, like the degree of intonation and pausing and emphasis, which is much more continuous in character. And so actual language has both. Right? It's a blend between both kinds of things. And the two influence each other, right? And certain languages are tonal, and you have tones that are discrete, but also can be modulated for another level of effect by someone who actually has mastery of the language. They don't talk like a robot, right? So, good, that's reality. Does that help us pick a loss function? And the standard answer is, well, do I have anything off the shelf that can handle that combined complexity? And before that, you say, does my data that I have for training reflect that combined complexity? And thankfully, the data helps you out here, which is that in every language known to human beings, the actual written transcriptions that one has access to do not capture the full nuance of what was said. And in fact, written language is its own thing where you suppress all of that nuance in the writing. So the writing is like only a hint of what was actually said in a play. So the data you have, what is it like? right? The data you actually have is discrete in language. You have characters, right? You have words. You do not have continuous things in your data. So you say, great, even though reality is some combination, it's actually like classification as far as your data is concerned. So then when it comes to picking your loss, what you do is you say, I'm going to look at a standard classification type loss. And what's your go-to loss for classification? Yeah, it's a cross entropy, right? Cross entropy loss. So you say, okay, just use cross entropy. So with cross entropy, you say, okay, great, I'm going to use cross entropy. What do I need for the inputs to cross entropy? Depends. You can think of the inputs as being scores. You can think of the inputs as being probabilities. However you do it, you need to have the representation be compatible. And by that compatible representation, it means that the output here basically effectively has to tell you what is the probability of any possible word. So the input is start, and the output is a probability distribution in spirit across all the possible words you could output. So thinking about the loss tells you you need to do this, because that's all you know how to do. Okay? So great. This question that you asked about the loss actually brings us to another problem, which you saw in the discussion, and you have in the homework, which is if the native output here is actually, the thing that's being trained is actually a probability distribution, when you run this during inference time, during actually like generating something, how do you feed this thing in? What do you feed in? Do you feed in a probability distribution? Does everyone see the question? Like, for training, the native output of this thing, the thing that you can train, has to emit a probability distribution, because cross-entropy loss demands it. But you want to use this autoregressively, and why do you want to use it autoregressively? You want to use it autoregressively because, in a sentence, things that you emit, you might have many different possible things you can emit. That's fine, but they all have to be grammatical. So you have to have the right internal structure in the thing you emit. So now the question becomes, can you actually emit a probability distribution and send it in over here? You could do that. I mean, it's nothing stopping you, right, to choose this input to be a probability distribution. But there's a problem, because for actual use, you have to actually emit a specific thing. You can't emit a probability distribution on words, another probability distribution on words, another that doesn't serve the application purpose, which is to print something on the screen. Everyone see this issue? So you have choices of what to do. One choice you can do is just pick the highest probability thing, which is the normal thing you do in classification. So if you pick the highest probability thing, and that's how you're actually going to output stuff, then the actual thing you picked, the highest probability thing, is what you stick in over here. Okay? You could also pick, say, hey, if you give me a probability distribution, I should pick by actually rolling that die and sampling from it. So if you tell me there's a 50% chance of this and a 50% chance of this, I should just toss a coin and say whichever one it comes out. That's also completely reasonable in the context of generating something. But the important thing is, however, whatever you actually output, you have to actually put that in as the input here. And what you saw in the discussion was that, hey, if these things are going to be probability distributions, and you're going to actually generate an entire sequence, and there's nothing that's forcing you to be very real time about it, you could actually keep a few possibilities and keep going, and then see what's the best overall possibility. Okay, by looking at the log likelihoods and summing them up, because this is doing something greedy, and maybe the model can't actually foresee everything that's going to happen, and you want to not get painted into a corner, right, of making of earlier choices. So that you saw in the discussion, you have it in the homework, is called beam search, where you You could enumerate all possibilities, or you can keep a finite set and work with it. So in that, there's the issue of, okay, if you think of them as probabilities, the longer this thing gets, the lower the probabilities go, right? Because you have to think about how do you combine probabilities. Standard way is think about how you're doing the generation. If you're going to roll dice every time, then the probabilities just multiply. But when probabilities multiply, they always get smaller. So if you're going to pick the highest probability thing, you're going to be biased towards choosing short things, which might be good for your application, or it might not, depending on what you're trying to do. If it's not good for your application, you can normalize by length. Right? Take the nth root of the probability for n long thing. So lots of choices. Really more a topic for natural language processing than here. But that was a long answer that comes from your question of what's the training loss. But you should see how everything just follows. You make a design, you have a question, you have to answer that design choice. Once you answer that joint, other questions emerge. Just follow that and make design decisions. Yeah. Yes. So the question is, if you're going to output something, remember, you have an actual task, right? Which is you have to emit strings. And if you want your strings to be all the different strings from the dictionary, of possible words that are coming out of the dictionary, you need to be able to have that be a possibility. Does everyone see that? Like, that's just what you're trying to do. If you're going to use a vocabulary, you have to be able to emit stuff from that vocabulary. You could say, well, that's very memory intensive. And then the answer to that could just be yes. Right? It is. You could have a smaller vocabulary. So for example, you could choose to say, maybe instead of emitting words, I just emit characters. One ASCII character at a time. Then your alphabet size is much smaller. But then maybe that's not the natural granularity you want. And that complexity you have of keeping track of everything just shifts into the state. Like you got to track what word are you spelling so far into the state. Any more questions on this basics? That took longer than I expected. Yeah. Great question. So if you say that, suppose you don't have a language problem. Suppose your problem is something different. Let's think of another problem. Suppose your problem is you want to have a robot do a trajectory. Okay? So your input is a linguistic description of please dance in a circle. Right? And the output is a sequence of motor commands that you give to the robot to make it execute that maneuver. That's the question? The spirit of the question? So in that case, what you would do is the architecture for sequence to sequence remains identical. Right? It's still the same architecture. The natural output you want is something that's continuous. So you have a desired trajectory that you want to follow. So you have an actual set of real numbers, vectors that you want. So you have to choose a loss that's appropriate for your problem. So you could, for example, just throw in squared loss here as a default kind of regression type loss. And then the same thing applies. Do you send in here as the input the trajectory you want to be on? Or do you say, where did you actually end up going? You see? Same thing. You want to mix them up a bit during training. So this is where the robotics context and the RL context, you can see how this is very, very related for control of a robot. The robot example also brings up that in some sequence-to-sequence problems, you actually have a third sequence, which is a contextual sequence. So you have an encoder, and then you have the decoder has another part of context that's coming. So in the robot case, it would be what are your sensor measurements for your robot, right? And so if that's the case, your decoder would have additional inputs that are coming in. And everything still just formally just works. Okay? Good. So you understand the basic picture of what's happening here for this sequence-to-sequence model. And now let's talk about what's wrong with it, right, for many practical applications. So when you see sequence-to-sequence, a part of your mind should think this, what is the convnet or image analogy of what I'm doing? Okay? So you say, in the context of images, what this would correspond to is something that takes an image as input and has an image as output. Everyone see that? Like, sequence is like an image. You weight share across an image. You weight share across the sequence. So the output being a sequence means the output is like an image. And so you saw that when you have an image-to-image problem, that there was this architectural choice that happened, which was the UNet architecture, right? And the idea of the UNet architecture was the UNet architecture said that maybe to get the details of the image right on the output, you need to have access to the details of the input image, or the process details of the input image, right? Because some things are kind of global, and other things are local. And in the UNet, you saw, if you tried to just do the image-to-image problem without the UNet architecture, you end up forcing everything that needs to come through a small bottleneck, which might not have all the information you want, because it's mixing details with the big picture. Everyone remember this? So here, this place is the bottleneck. From the encoder, everything about the input is being forced to be squeezed through this bottleneck and handed over to the decoder. So this is like a pixel-to-pixel problem, image-to-image problem, where you don't have the UNet architecture. You have no way of looking at the local information in doing what you're trying to do at the decoder. Okay? Everyone see that? So there's a need, right? Problem. We have no way for fine-grained information to come to the decoder except mixed together with coarse info. So in images, in many image-to-image problems that one has, there's a natural correspondence that tells you where to look. Okay? So when you're many image problems are like, for example, semantic segmentation. So you want to say, at this pixel, what category of object is there? And so you know very intuitively that the local information, the fine-grained information that's relevant for this pixel is in the original image what was there at this pixel. The locations map to each other. Okay? Is that good to everyone? Everyone gets that? We just said one of the problems in languages is different languages have different word orders. So we have a bit of a challenge, right? If you try to use a straight UNet style architecture where the routing is something which is determined, of information is determined in advance, right? That's what a UNet does. The routing of the information is just done in advance. That's not going to work because you don't know how to route the information in advance. It's context dependent, right, for the specific sentence. Some sentences, you know, the required place to get this output correct might be one position in the input sentence for some sequences, but for other input sequences, it'll be a different position to look at. Everyone clear with this problem? So, challenge. We don't expect any static routing of info to work. Has to be context dependent. So what is static routing? Static routing is, down in the level of details of implementation, is you index into an array and you know where to index. Okay? This is like indexing into an array at a known position. So this doesn't work. So this leads to the kind of design question. The design question is, we need some kind of structure where we can achieve our goal of having information at the encoder being put into that structure so that we can get it out at the decoder, but get the right piece of information for every position. Is that clear? Question, yeah. Yeah, that's a great question. So let me answer that question before I move on to this one. So in general, the question is that if you're going to be learning a machine translation system, and you want to translate from, let's say, English to French, then can you train it on just English to French data? And the answer is, of course, yes. You can always train it end-to-end on the specific problem that you have. So then your question is that, would it be helpful to also have, could you get any value out of English to Spanish data? Right? Am I getting the spirit of your question? And the answer, you feel like it should be helpful because English to Spanish data is telling you at least something about English, right? Even if it's not telling you anything about French. It might tell you something about French too, because Spanish and French have some shared history. But it's definitely telling you something about English. So it could help the encoder. So you could imagine training one encoder that works, and you want different decoders to work with that same encoder, and maybe you can learn some regularities better that way, because you'll have access to more data. Right? Everyone see that? Yeah, it's a good point. Where this becomes really relevant is when you want the translator from English to a small tribal language for which you have very limited data. So there you might not have enough data to do the direct thing. But maybe there's a hope of, if you have a, all languages to all languages translator that you try to build, that you learn the right representations, and you can actually fill in translations for languages for which from pairs of languages for which you have no data at all. Right? And in fact, people do try to do this. I think Google has a huge project where they're trying to build a translation system that tries to exploit this. In particular, to be able to better serve under resourced languages where you don't have that much annotated paired data. Yeah, it's a great question. It does also relate to this problem of if you have all this variety, you definitely need to have some more dynamic way of getting ideas of what the local context is. Right? So now what I'm going to do is I'm going to move this over. And talk about this attention mechanism. But I'm going to talk about it a little bit differently than most treatments I've seen. So I'm going to talk about this in a way that kind of we're going to build towards this by seeing how you could have come up with it yourself. Okay? Instead of, oh, look, there's this wonderful paper, we introduced this idea. Let's see how you could have come up with it. So you find yourself in this problem. Okay? You want a way to be able to find information that the encoder might have put, like a UNet, but you can't look in a fixed place, right? So you have to ask yourself, do you know any data structure that you can think about, just as a conceptual thing you want to build, in which instead of indexing by position, you index by something else, right? Anyone want to volunteer something? A dictionary, right? Hash table. So you say you want something like a hash table or a dictionary. Because then you can ask for something and get it, right? You want sort of something you can index by key. Okay? Keys and values. So now, let's think about how you do this. So first, we say, okay, this is our goal. Can we do this? So we want, we'll call it attention. We want is something like a hash table, except it has to work with training. Okay? So training is going to be doing backprop. Okay? So whatever it is, it has to be differentiable. Some kind of differentiable hash table. Right? And now there's going to be, like, we're going to go through a sequence of ideas of what you can try to do, and those ideas will break, and we'll try to fix them, and we'll keep iterating our fixes until we get something that might work. Okay? Which is how you should approach solving problems. Try something, breaks, fix it, keep going. So I call it idea -1 before we start. Okay? Let's look for an exact match. Of query Q to a key and return value. This is like a standard hash table. Okay? So how do you use a hash table, right? You have key value pairs and you stick in a query. Does everyone see that? Like, remember, and you look for a match for your query. Is your query in the dictionary? If so, return the thing. Right? Let's try doing exactly that. So now, what's wrong with this? You think, if you want to add some way for this particular thing to query a hash table, right? It's going to be emitting a query. Some kind of query is going to come out, and some kind of value is going to come back. How is that query generated? There'll be some MLP inside this neural net that's supposed to emit the query. Right? Like, how do you emit anything? Some MLP. That MLP will have some random initialization. Right? Is that clear to everybody? So, at initialization, will anything match? Ever? The answer is no. Right? Nothing will ever match. Do you see that? Does everyone see that? You randomly put in a query that's from a random initialized MLP. There's randomly initialized key value pairs in there with keys. Nothing is ever going to match. So you're always going to return not found if you follow this -1 approach. And then you will have no gradients, and you'll have no way to learn to find anything. Okay, so we can't actually accept having something which is actually like a hash table. It has to be some kind of approximate hash table. Otherwise, you'll never get any matches. Is that clear? Yeah. Oh, okay, yeah, good. So let's just go back to this. Sorry, I'm going to have to keep going back, right? So remember, we're trying to approximate a unit, right? And so the idea is we want to use something like a hash table, which means that each of these points in the encoder are going to stick something into the table. Just like a unit, you have to look in a certain place, right? So instead of a certain place, we're going to look inside of a hash table. Each of these things will have stuck something in there, some key value pair. And you have to get something to come out. So the hash table for the case of this kind of attention, it's called cross attention, if you won't care, but is built by the encoder. And it's going to be used by the decoder. Okay, so this now goes to idea 0. So idea 0 says, instead of looking for an exact match, let's look for best match. You know, closest, let's say. Okay, so we change it from exact match to best match. So we've solved the basic problem of not returning anything. Like, there'll be something that's closest. So we'll return something. So what's the problem now? Remember, we have to train using backprop. Yeah. Oh, closest? So how do we define closest? So we can always define closest. So everything's going to be a vector. We can look at closest in Euclidean distance. Or inner product. Your choice, doesn't matter. We have a similarity measure. We don't have a problem with defining this. Like, you can write the code to do this, right? There's no problem with writing this code. It will run. The question is, does anything go wrong as you try to train it? Yeah.
Well, what are the gradients?
Yeah, gradients. Do we have gradients? So we have a gradient on values. Yes, on values. Because we return a value, right? And so we can pass the gradient for that value. Right? We'll get a value. We can ask to change that value. But we have no gradients on queries, Q, or keys. Why do we have no gradients on queries or keys? The reason is that, what's a gradient? A gradient is, if you change it a little bit, how would the output change? So you're doing the closest match. In the closest match, if you change the query by a little bit, would the closest match change? Typically not. Everyone see that? Typically no change. So the gradient on the query is 0. all the other keys and values that were chosen, of course there's no gradient on them, because they weren't even chosen. Is there a gradient on the key that was actually matched to? The answer again is no. Because if that key was a little tiny bit different, would you have matched to someone else? No. You still would have matched to this. So no gradient. So no gradients, meaning actually zero gradients. But you never have a gradient. So you can never learn a better Q or K system at all. You might learn better values, but you'll never learn like who to match to, which is our whole point. You need to learn where to look. So this is the fail. Okay, so how can you fix this? Yeah. Yeah. So what you can do is to say, do a weighted average, right? So now we're saying even an approximate hash table isn't enough. We actually need a softened, like a blurry approximate hash table. To return something that has not a specific thing in the hash table, but like a blur of values in the hash table. Okay? Because if you get a blur of values, so do a weighted average. So what does that mean? I'll make it concrete. Like look for closest spiritually matches, plural, very important, plural, of query to keys, plural. And return a weighted average of values. Okay? Plural. Yes, the question becomes, what should these weights depend on? Okay? So first thing, before we talk about what these weights depend on, you should see that at this point, you want to have, so goal is to have gradients on everything, right? You need to have gradients on everything. So, do we have any hope of getting gradients on everything? Well, what do we need? We need it to be the case that if the query was a little bit different, that we return something different. Does everyone see that? You have to return something different. Okay, that instantly rejects certain possibilities. So if you think you want for the weighted average, just like let me equally average together the closest matches, and you set your closest matches to be the 5 closest matches, you're stuck in the same situation you were before, which is that if the query were to change a little bit, your closest 5 matches would still be the same 5 matches, and their average would be the same. Everyone see that? Okay, so you can't do that. The weighting has to depend on how close they are, right? Must depend on closeness in some way. It has to be that something closer gets more or less. From a gradient point of view, it doesn't matter. Obviously, one is more reasonable than the other, but something closer has to get more weight in this weighted average than something that's further away, because that's what will give you a gradient on the query. Everyone see that? So if you do this, you will get gradients. Yay. Gradients on everything. So now you have a possible workable idea. Now you have to take this possible workable idea and concretize it. Okay? Like make it specific. So what are we going to return? We're going to return a sum, some kind of sum, of some kind of similarity measure between the query and the key, and use that to average together the values. So now the question becomes, do we have anything sitting off the shelf, that's already programmed for us, basically, that we can use to do this? And the answer is, yeah, we do, right? Which is, this feels in spirit like a softmax. Does everyone see that? Because a softmax gives you kind of soft average, kind of like a softmax is almost like an argmax type thing, except it's softer. So we can use softmax ideas. So let's make it all explicit. I'm going to erase stuff here because I don't want to lose this on the board. So I can use this I use some kind of coarse similarity function. Some kind of coarse similarity score. So I have a couple of, if you think about it, in the context of ML, you have two candidates that are sort of sitting as your go-to default ways of measuring similarity, right? Two candidates. One is I can take my query and take the inner product with a key. Like inner product. Good old correlation, right? The first similarity thing you learn. Correlation. Or the other thing you have is like a RBF. RBF style. But you look at the RBF style, right? And you remember right? They just have that. So if you think that these Qs might be normalized, like they might have some norm on them, this isn't the interesting part of what's going on. And this is also basically also rooted in correlation as a similarity measure. So we can basically, let's go, both of these are kind of doing the same thing. We know we're going to be using some softmax idea, because that gives us a nice kind of natural way of averaging things that are like probabilities, right? So, and softmax has a connection to RBF because of the exponential. So we'll keep that in our mind, right? Okay, let's keep that in our mind. And maybe let's go with this. Let's use, for an intermediate value, I'll call it EI, the similarity between Q and query and key. Now, there's a question here of units, right? Like, what do I want to have some kind of standardized units or not? So it turns out that if you look at it and you say, well, how long are these things? So if the query and the key are both d-dimensional vectors, there's a question of whether I want to actually normalize things in an appropriate way with the dimension. So turns out it's good to do that, because otherwise what will happen is that the inner product will change in its relative absolute magnitude based on how big the dimensions are. So we can just, for purposes of normalization, we can take this and normalize it by the square root of the dimension, d. Why do we normalize by the square root of the dimension? If you normalize by the dimension, you can never get this core similarity value to be bigger than 1. Does everyone see that? But you kind of want, maybe in the context of a softmax, remember we're going towards a softmax. For a softmax, if you want it to put all of its probability mass on one thing, the score has to be infinity or big. Everyone see that? So if I cap out the scores, I will never be able to put all of the mass on one thing. And that's probably a big reduction in my expressive power. So I can't put d down here as a normalization. At the same time, softmax will tend to do that for big values anyway, so I need to normalize by something, or I'll just randomly get a big value. Right? If I take a uniform, if I sample from a distribution that has values that are big and small, oh, I'm over time, then I'm going to have a problem. So this is like the right in-between thing, which you can think of as, if I think of this is filled with IID entries, think of this is filled with IID entries to start with, then this product will be on the order of square root. Right? Because the sum of IID things has order square root of the number of things you're adding together by CLT. So this is the normalization. Next time I will continue from here and tell you that you just do a softmax. And this gives me my weights. Okay? This is how attention can be built out of the idea of a hash table. So with that, I will end a recorded lecture.